Okay.
All right, thank you very much. So I'm going to be talking to you today about a model for speculative evaluation. So I don't know how your 3rd of January was last year. Mine was quite nice. Went into London, went to the Tate Modern, met up with my brother and his kids. They had this fabulous exhibit in the Turbine Hall of a bunch of swings. And I was on the train back, you know, doing what you normally do, checking Twitter on my phone, and Twitter! The Spectre has happened! Right, and this was my hot take on Spectre on the day, was, first of all, oh mate, MG, this is really serious. And secondly, normally there's a kind of smug feeling of satisfaction from somebody who works in the kind of formal methodsy bit of the world. Anytime one of these things happens of, if only you'd used, and now you insert some horrible combination of like separation logic and temporal logic, and you would have solved this problem. And that wasn't my reaction in this case. My reaction was, I don't know even how to talk about this. I don't know how to model this attack, never mind, you know, proposed mitigations against it. And so the kind of reason for the OMG part of this is that the Spectre is essentially a mechanism for bypassing any dynamic security check. And in particular, you can bypass the dynamic security check of array indexing. And that means that you can index arbitrary points into an array way off the end of it and read any address in memory in the current address space. You know, you might note that it's the browser vendors who are like throwing their hands up about this. And that's because we're in the business of sandboxed execution of untrusted code. That is one of the main things that a browser is providing for you. And so the fact that you can exploit this from inside JavaScript is really quite worrying. And the feature that they're exploiting there is speculative evaluation. So this is a hardware optimization that's meant to be just down at the microarchitectural level and not visible at the architectural level. Right, so what are these kind of optimizations? Well, here's a simple optimization. So a lie that we tell to kindergartners when they're learning to program is that computers execute instructions one after the other. So we give you a program like this that increments x and then sets y to be 1. And right, okay, this is the execution that it has. And that's the model that we give to people up until sometime at the end of their undergraduate education in computer science. And where you've got 3 actions here, one of which is you read x and you might get 1. And then you write x to be 2, and then you write y to be 1. But that's not what's actually executed by hardware. So hardware is perfectly capable of spotting that write to y of y to 1 doesn't depend on the value of x, and so it's perfectly capable of executing it first. So there's no dependency between any of the actions on x and the action on y, so it can get reordered. And that's fine if you couldn't spot that lack of dependency. And for single-threaded programs, you can't. So for quite a while, you know, every model of programming languages was based on sequential consistency. But unfortunately, the instant you've got shared memory concurrency in, this goes out the window. And that's resulted in, there's an entire cottage industry this century of people developing weak memory models. So kind of kicking off with the Java memory model by Pugh et al. In about 2005. And like C11 has got a very similar style of model. Okay, so that's what's happened with instruction reordering. Right, well, what's happened with speculative evaluation? Well, it's kind of like a similar story of like, well, we've got this lie that we tell people that you've got an if statement there, and one of the 2 branches is going to get executed. Ha, ha, ha. Right, well, first of all, that's, you know, we've already seen that there's an untruth there because that right of z does not depend on the right of y, so there's a lack of dependency. But also, there is actually an execution in which the right of 2 might happen, And then the hardware rolls back and goes, oh, oops, sorry about that. We didn't actually do that right of 2, and instead we did the right of 1. So that's the optimization which current hardware currently does. But compilers get in the way even more. So most hardware will not do this, but your average compiler will, and will spot the fact that that right of z to 1 is happening on both branches. And so it'll move it outside the if statement. And at that point, it's now floating. And there's no control dependency from reading x to 1 to writing z. All right, okay, so we've got a similar situation of, we've got an abstraction. That abstraction has leaked, so, in practice, we know that user code can observe this behavior. Right, so what are we going to do about it? So one possibility is to look to see what kind of language model you could provide that's a high-level model, abstracts away from as much microarchitectural detail as we can, but still actually models speculative evaluation. And so one of the reasons for doing that is Spectre. So we'd like to at least be able to capture Spectre and Spectre-like attacks. So a very simplified version of what Spectre does is you imagine you've got a secret and you've got a runtime security check that's going to determine whether you're allowed access to that secret. And for the attacker, that security check will always fail. So it's always going to go down the else branch, and therefore you would think not get to read the secret, and so it would be safe. Right, okay, so here's an example execution. You look to see if y is true, and if you can read the secret, then you set x to be the secret, otherwise you set x to be 2, blah, blah, blah. Right, okay, so in that execution, the read of the secret might get executed and then rolled back, but it won't happen in the regular non-speculative execution. But the attacker would still like to know whether the secret's 0 or 1. So if they can leak 1 bit, they can probably iterate and leak an arbitrary number of bits. Right, so here is your Specter attack. So you look to see if you can read the secret, and if so, you use it as an array offset, and now you look to see whether you've touched that bit of memory. And if you've touched that bit of memory, you set x based on which bit of memory has been touched. Right, okay, and so now that's got the execution that allows information to flow from the speculative world into the non-speculative world. So there's an information flow attack there if you can introduce an implementation of the magic there. And oh dear, that's what Spectre did. And so now the advantage of having the high-level model is that we can reason about the ability to detect whether an area of memory has been touched without having to reason about the low-level timing and cache behavior that actually causes that to be implementable. Right, so those pictures that I've just shown you, those are actually formalizable. So there is a formal model that's sitting behind that that's based on partial ordered multisets. And using that, we can build a compositional semantic. So if you're familiar with the way that C11 semantics looks like, then there's not that much of a surprise there. And we've got examples of how you can use that to model Spectre and Spectre mitigations and attacks on transactional memory. Right, well, one thing that was funny about this is that during this work, we realized that, in fact, the model's got some odd information flow properties that are just about the compiler optimizations, not the hardware optimizations. And so if you look at that program there, we've got a multi-threaded program that's got 2 threads, one of which is forwarding x to y, and the other one of which is looking to see if y was non-zero, and if it is setting x to be 1, and otherwise it does the kind of like Spectre kind of stuff. Right, okay. So you would think there is no way that write to z to 1 can happen. It's like, what? How did you end up down that branch? Right, well, the problem is that if the secret is 1, then the compiler can spot that all three branches are assigning x to be 1 and can float it out of the if statement. And so now the dependency from y to x isn't there anymore. And that means you can actually get that first execution. Whereas if you try doing it for anything other than the secret being 1, right, there's now a dependency between the read of y and the write of x. And that means you end up with a cycle in the model, and those kind of cycles aren't allowed. And so that execution can't happen. And that means you've got an information flow sitting there. All right, well, okay, so that's the theory. But that might just be an artifact of the model. So, who cares whether you can attack my model or not? Right, what we care about is, can you actually attack real compilers? So at this point, I'm going to introduce Craig, who will talk about that.
Right, is this on? Yeah. Okay, so as Alan said, the main question we're trying to answer now is, our model captures all these attacks, including Spectre, Prime and Abort, other existing attacks. And these existing attacks, they exist in the real world. We can implement them. Can we do the same for these attacks on compiler optimizations? And in our paper, we definitively answer this question as yes. We can implement these compiler attacks in the real world on real compilers like Clang and GCC, with an important caveat that we have an unrealistic attacker model, right? So we're able to attack Clang and GCC, but only when the secret is a compile time constant, because that way the compiler can reason about the value of the secret and perform optimizations based on it. But at the same time, we need the permission check to be dynamic so that the compiler can't optimize away code that would fail the permission check. So obviously this is not a realistic attacker model that anyone's going to be worried about or issuing a security update for. But nonetheless, we feel that this is an interesting attack, at least from an academic perspective, because no one's really done attacks on compiler optimizations before. So to put this a little more concretely, this program at the top here looks a lot like the program that Alan showed you earlier. And we see that the code generated by GCC, based on when secret is or is not 1, is very different. So on the left, we have the code generated when the secret is not 1. And on the right, we have the code generated when the secret is 1. And in particular, on the left, we see that GCC emits the write x before the read y, whereas on the right, there's no conditional because there doesn't need to be a conditional, and then GCC emits the read of y before the write of x. And normally you wouldn't be able to observe this, but in order to observe this, we're basically going to add another thread which just does x equals y in a loop, and that will allow the attacker to be able to spot this load store reordering. So to make this attack a little bit more practical, we add a small delay between the write x and the read y, which increases the probability that the other thread gets a chance to jump in and do y equals x. We found that we can insert up to 30 straight line instructions in between the write x and read y, and GCC will still do the load store reordering that we need. Then we can repeat this attack to leak multiple bits of the secret and also to perform error correction. And as a result, we can achieve a bitwise accuracy of 99.99% at 300K bits per second for this fictitious attack. We also implemented a similar attack on dead store elimination, which works against both Clang and GCC. And for that attack, we achieve a bitwise accuracy of 99.99% at 1.2 megabits per second. So in conclusion, in this paper, we presented a compositional model of program execution that is sufficient to capture both existing attacks like Spectre and Prime and Abort, as well as new attacks on optimizing compilers. We have obtained experimental evidence that these new attacks can be carried out, but only against compile time secrets, which is not a realistic attacker model. As a final side note, we were interested in whether these new compiler attacks can be applied against JIT compilers, because JIT compilers have access to potentially much more interesting secrets at compile time. Thankfully, depending on your perspective, we were not able to do this because today's JIT compilers simply aren't aggressive enough with their optimizations to enable us to conduct this attack. But maybe in the future, if JIT compilers get more aggressive, we'll have to start worrying about this. In conclusion, all of our code is open source and available at this URL, and we're happy to take any questions.
Thank you very much. Anyone with questions, please step forward to the mic.
Jonathan Lee, Microsoft Research. Lovely talk. One question I have. So it sounds like a lot of your modeling is assuming that the disclosure gadget you're going to use from the speculative execution is based on accessing memory somewhere. So it sounds from your model like the disclosure gadget that you're using for your speculative execution is fundamentally linked to memory accesses. And there are a number of papers published at this point that show that there are other ways of getting information out of speculative execution. For example, you can look at the execution units that are used, or you can touch other internal structures in the CPU. I wonder if you have any thoughts about whether you could generalize the work you've done here to capture that.
Yeah, so the examples I've given here are entirely about shared memory concurrency. The approach we've tended to take for other forms of communication, so for example for transactions, is to introduce new forms of events. So the events that I've given here are just the read and write events on memory, whereas for transactions you also get commit and begin transaction, commit transaction events. And that style, so far the examples we've tried it on, we've always managed to invent a few new events and come up with what the invariant is that those events have to satisfy, and use that as a way of abstractly modeling the kind of style of attacks. So we've done transactions, we kind of did riddle on a blackboard. Okay, are there any other ones?
We modeled fences, kind of.
Oh yeah, we did fencing as well, and the stuff about mitigation requires fencing. So I mean that's a slightly unsatisfactory answer, because it's it required us to do custom stuff each time, and we don't have a formalization of how to do that custom stuff. We've just observed that in practice we've been able to do it each time.
Thanks very much.
Thank you very much again.